Let's continue on with the last section that we're covering in this chapter. 5.4, Sampling Distributions and the Central Limit Theorem. Let's talk about the different types of sampling distributions. In this section, you will study the relationship between a population mean and the means of random samples taken from a population. So take a look at this type of sampling. We see that there are two different types of samplings, and they have nothing in common, but there's possible to have some overlapping within some groups in the samples. A sampling distribution is a probability that a distribution of sample statistics that is formed when a random samples of size n are repeatedly taken from a population. The sample statistic is the sample mean, then the distribution is the sampling distribution of sample means. Every sample statistic has a sampling distribution. Properties of sampling distribution of sample means. The mean of the sample means mu sub x bar, or just mu x bar, is equal to the population mean. So we're saying that they're the same. The mean of your samples and the mean of your population, we're going to treat them as the same. 2. The standard deviation of the sample means, sigma x bar, is equal to the population standard deviation, sigma, divided by the square root of the sample size n. The standard deviation of the sampling distribution of sample means is called the standard error of the mean. All right, so what makes this different is this here. This is what makes this section unique, not chapter, section. This will allow us to work with a standard deviation that is created from our sample means. And to do so, or why we do this, is because of our new concept that we will introduce, the central limit theorem. This theorem describes the relationship between the sampling distribution of sample means and the population the samples are taken from. The central limit theorem is an important tool that provides the information you will need to use the sample statistics to make inferences about a population mean. All right, so we see here that when we have any population, we have this first picture. We see how if it's larger than 30, we can kind of smooth out the information and get this bell-shaped curve. Versus when we have a sample, we need to make sure to adjust the standard deviation, mainly because of these tails. For any n, we can smooth it out so it can become more like a normal distribution. And we'll see in the future that as our samples are smaller, our tails are off, and thus our proportion can be also off. The central limit theorem. 1. If a random sample of size n, where n is greater or equal to 30, are drawn from any population with the mean mu and a standard deviation sigma, then the sampling distribution of sample means approximates a normal distribution. The greater sample size, the better the approximation. That makes sense, right? And what we're saying is the bigger your group, the more perfect, I guess you could say, or the more bell-shaped your curve is. 2. If a random sample of size n are drawn from a population that is normally distributed, then the sampling distribution of sample means is normally distributed for any sample size n. In either case, the sampling distribution of sample means is equal to the population mean. So mu x bar is equal to mu. The sampling distribution of sample means has a variance equal to 1 over n times the variance of the population and a standard deviation equal to the population standard deviation divided by the square root n. So it gives us the variance and the standard deviation. Let's do an example. So we're pretty much taking the same idea as before. We have some bell-shaped curve. We have a mean. And what's different is our standard deviation from our sample is going to differ from that of our population. So let's go ahead and see this in an example. A study analyzed the sleep habits of college students. The study found that the mean sleep time was 6.8 hours with a standard deviation of 1.4. Random samples of 100 sleep times are drawn from this population, and the mean of each sample is determined. Find the mean and the standard deviation of the sampling distribution of sample means. All right, so we want to find our mean from our sample means. We also want to be a standard deviation of our sample means. All right, we were told that the mean sleep time is 6.8 hours. So our answer would be 6.8. Our population mean and our sample means will be the same. Now, our standard deviation, that will not be the same. We have to do a bit of work. We were introduced to a formula, we have it right above, and we're told that the standard deviation of sample means is sigma divided by the square root of n. So we have a sigma, 1.4 hours. You covered up the decimal, 1.4. And we were also told that we have a sample of 100. So let's use those pieces of information. So my standard deviation is 1.4, and I have to divide that by the square root of 100. We punch this in our calculator. Square root of 100 is 10. And we get 0.14. So therefore, our answer would be 0.14. 0.14. We have answered our question. Probability and the central limit theorem. In a similar manner, you can find the probability that a sample mean given the formula. So nothing has changed. The only thing that's changed is our standard deviation. Now we have to use our new formula. And again, this is just our formula. We've seen this before. It's our z-score. Well, we can find a z-score just as before as long as we make that adjustment for our denominator. Let's do an example. The mean room and board expense per year at a four-year college is 10,453. You randomly select 9 four-year college students. What's the probability that the mean room and board is less than 10,750? Assume the room and board expenses are normally distributed with a standard deviation of 1,650. All right, let's draw our information. Always draw your bell-shaped curve. And we have a mean. Our mean of sample means is the same. We're told the mean is 10,453. All right, and our question is, what is the probability that the mean room board is less than 10,750? So we want to know what's the probability that's less than 10,750. So those values. That's what we're looking for. All right. Well, we will follow the same process as before from our previous sections, but we have to make one small adjustment, our new standard deviation. We know to do this, two key things. The word sample is thrown in. In the previous sections, we never discussed the size of your sample. We were just given a mean and a standard deviation. Now we're being thrown in a new piece of information, our sample size. And you know to do this also when your sample is less than 30. So those are key things to let you know that this is a 5.4 type problem versus a 5.1, 5.2 type problem. So is your sample less than 30? Yes. So we have to go ahead and use this, our new formula, which is your standard deviation divided by your sample size. We were told that our standard deviation is 1,650. So we have 1,650 divided by the square root of our sample size. We were told we have a sample size of 9. Let's punch this in our calculator. So we have 650 divided by the square root of 9, and we get 550. So that is our new standard deviation. Sigma x bar is equal to 550. All right, now we go ahead and enter information as before. We want the probability from the smallest value up to 10,750. So whether using a calculator or Excel, the difference is your standard deviation. You don't use that default standard deviation. You have to use your new calculated one. All right, so let me punch this in, see what your answer should be. And we should get 0.74. Oh, 0.705401511. So if we round, it'd be 0.71. Now it's a probability that the room and board would cost less than 10,750. All right, that's it for this section. Again, the only thing that's different and what we introduced is our standard error sample standard deviation, which we have written several parts in our in our lecture. So this is what's new. This is what makes it different. And again, how do you know you're dealing with this type of problem? You're going to be given the sample size, and this is when our sample size is less than 30. Because we need to make up for the fact that our sample size is smaller. So this is a way to adjust your information so that you can use your information for a larger scale. All right, thanks.